Now the next step is to connect this to a ping board. So what we'll do is we'll go and make a new project. I've already made a new project called NTT wrapper. So this wrapper is basically for connecting our IP to the ping board. So basically here we have done 16 bit and 16 inputs and 4 bit. Now let's do for a new example. I'll open a new project. We'll do it for 16 inputs and each input 4 bit wide. We already have made the IP there. And here we are going to the board. We'll have to select boards and select PYNQ-Z2 board here. That's where we are going to work. I'll close the old IP. First, we'll go and import the IP, custom IP which we already made. We'll go to IP repositories. We'll go to 75 IP repo, and 16.4 is our IP. So I'll select this. You can see one IP is already there, which is NTT 16.4, which is 16 inputs and each input is 4 bit wide. So our IP is added to the design. We'll create a block diagram now, and naming convention can be given by your choice, but we'll have to remember the naming convention so that we can avoid confusion at later time. Here we have a block design and we can create blocks and do the connections automatically. Let's first add a zinc processing system. This is a processing system in PYNQ-Z2 board, and this will run the block automation. So now we can add whichever IP we want and connect it to the particular processing system. The IP we're going to add is entity IP. This is customer IP. And here in Vivado, we can do the connections in an automatic way. This will do it for us. And here we can see new blocks are being added. This is added so that the connections take place properly. We'll save this. And now this is a block design. What we are going to do is we are going to create a HTL wrapper. So upon creating it, we'll get a Verilog code for this. That Verilog code can be used for synthesizing and generating bitstream. This is basically the Verilog code. We have created a wrapper for blocks and it is calling each blocks by itself. Now we'll generate the bitstream now. First step before synthesizing is synthesizing each and every block in the design. The processing system and the entity are the blocks we added. The other two blocks were added by Vivado itself so that the connections take place properly. Once these blocks get synthesized, once these four blocks get synthesized, the whole design gets started synthesizing. Now we can see that the bitstream generation is completed and we can see everything is synthesized and implemented as well. Now what we are going to do is we are going to export this particular block file. Here we have created this block diagram and we are going to export this and we are going to export the bitstream that got generated as well. We have to remember the naming here and we are going to export it and we are going to export the bitstream file as well. So since we have it's both of them, now we are going to work on the ping board. And another thing with ping board is that ping board cannot recognize the bitstream file without the HWH file. So we'll have to copy that as well. So all these three of them, we are going to use it along with the bitstream file and the TCL file. All these three things we are going to use it so that we can put the generated IP onto the ping board. Let's see the connection of ping board now. First of all, we have got jumpers here which we have to make connections appropriately. Here we have put it in the USB slot, and USB slot is this is for where the board is going to get the power from. We are going to give it to the USB slot here, and this USB is connected to the laptop or any other device. And here there is another jumper here. Here we will say where the memory is and where we have all the resources. For that we have put it on SD card thing, and we also put the SD card into the board. This Ethernet cable is also connected to the laptop here in this case. Now we'll first switch it off here. This light just shows the power is on for the board. Now the OS will reboot it. Once these four LEDs stop blinking, we can start working with the board now. Now that the ping board is connected, we'll set up a static IP for this device. We'll go to control panel, networking and sharing. And here this Ethernet is the ping board connection. We'll have to set up the static IP here. We'll go to properties and internet protocol version 4. Here we'll have to remember that the IP address of ping board is 192.168.2.2. So we'll have to set any number other than 2 here. I'm going with 1. Now after setting up the static IP, we'll have to go to network and we can connect the laptop to the ping board. Here we can see the Jupyter Notebook environment. Here I have already uploaded all the necessary files. .tcl is the design file, .bit is the bitstream file, and .hwh is the hardware handoff file. As already told earlier, a hardware handoff file is used so that ping board can recognize TCL and the bit file. For demonstration purpose, I have already opened a Jupyter Notebook here. Here for the example, I'm going to use 16 inputs and 8-bit, each input 8-bit wide file here. I'll open the overlay, and here we can see NTT 1680 IP, which we already created earlier, and this IP is the one we are going to be using here. Now I'll just give a name as NTT IP here so that we can read and write easily. The type is default IP. Now for the comparison of the computation time between software and hardware, I've written a code in software here. In Python, I've implemented the same algorithm as that of hardware. So as we can see here, the same entity algorithm is being implemented. Now we'll check the computation time. For checking the computation time, I'm using the time function. So we are going to start here and end here. After calling the function, it will display it automatically. For this input, I'm giving 16 inputs as that is the hardware file here, and each input is 8-bit wide. And in software, we did not worry about the width here. Also, the prime number is given as 171, and I also gave 12 factor as 2. And this SW software is the computation time in milliseconds. For input, I have given 1 followed by 15 zeros, so the output should be 16 ones. As expected, we can see there is 16 ones here, and the computation time is 36 milliseconds. If you run it for multiple time, it will settle around 30 to 35. Now, if you come to NTT IP here, this is the hardware IP, and here we can write and read here. If you're unsure about the offsets to use, you have to go to the header file, and this header file is available in the IP which we have created. If you go to that directory, we can easily find it. And here we have used 4 for inputs and 1 for Q and twiddle factor, and other 4 for output. So if you are unsure about how you have given the inputs and output, you can go to this particular file. This is also present in IP. Here, if you see, we have since each input is 8-bit wide and each register is of 32 bits wide. For every register, we'll have 4 inputs. So we have used 4 registers in total for 16 inputs, and the fifth register, first 8 bits are for Q, and the next 8 bits are for W. And you have to remember how we have done, or you can go to this file and check how we have given the inputs here. The other Other registers are just for output. We can directly read from it. The only problem is giving the input. Now we go back to the Jupyter file. We can see the first four are for inputs, and the input I'm giving the same here, one followed by 15 zeros. So each register will have four inputs. So first register will have one followed by three zeros. So this one is of each input is of 8 bits. So I'm going to give 8 bits of one only. So seven zeros and one here. So if you're not giving the input properly, we might end up with some error or may get unexpected results. So and this fifth one is for Q and W. First 8 bits for Q, and this is the binary for 171 which we use here. The next 8 is for 2. So we have given the inputs here and again use the same time function to calculate the computation time. So in these four offsets, I'm going to read it. So if I read, I'm going to get same output, and each register will have four output bits, same way as inputs. And here we have four ones, and again there are 16 ones in total. And this will have seven zeros before it, and it is not displaying because it's before it. Now, if you see the computation time, it is just 2.5 milliseconds compared to the 30 over here. If you run it for multiple time, it will settle in 2.54 or 2.55. So this just proves that the hardware implementation is faster than software.